Well, ladies and gentlemen, it is always a privilege to speak at Imperial College, but especially so on an occasion linked to Sir Ralph Kohn. Ralph is a real Renaissance man. He has been both practitioner and patron of music, science and medicine. And I welcome this chance to pay tribute to him and to thank him for the flattering half-truths which he has kindly said about me. I would just like to add, regarding the music, that when I was on Desert Island Discs, I chose the Razumovsky movement you mentioned. I also chose one of Strauss's 4 last songs to show you can do good work in your 80s. My topic is the night sky, and astronomy is, of course, the grandest of the environmental sciences. Indeed, the night sky is the part of the... Could we have the lights down a bit? It might be a bit easier if we could turn them down a bit. So I've got lots of pictures. Yeah. Even a bit more? Yeah. Okay. And astronomy is the oldest science except for medicine. And at the risk of annoying the medics here, I would claim it is perhaps the first science to do more good than harm. But it's also a science where there's been a great crescendo in the last few years, which is mainly owed to powerful telescopes in all wave bands, better sensors for faint radiation, and space technology. Equally important have been powerful computers, and armchair theorists like myself deserve little credit. I'd like to start off with a flashback to Newton. Newton was, of course, the greatest intellect of the last millennium, although a most unpleasant person, solitary and obsessive when young, vain and vindictive when he was president of the Royal Society. He famously showed that the force that makes the apple fall is the same that holds the planets in their orbits, and he must have thought about space travel. Indeed, this picture from the English edition of his Principia is still the neatest way to explain orbital flight. He calculated that for a cannonball fired from a mountain top to achieve an orbital trajectory, it has to be fired at 18,000 miles per hour, far beyond, of course, what was then achievable. And as we know, the first object to achieve orbit was Sputnik 1, which went up in 1957, followed by Yuri Gagarin almost exactly 50 years ago. And a few years later than Gagarin, Apollo astronauts brought back this picture, which has been iconic ever since for environmentalists. And then the moon landings. Neil Armstrong's first small step, only 12 years after Sputnik, and only 66 years after the Wright brothers' first flight. It was a heroic episode, and I cherish this picture signed for me recently by 7 of the Apollo astronauts. But after Apollo, the political impetus for manned spaceflight was lost. You've got to be middle-aged to remember it. Young people know that the Americans landed on the moon, just as they know the Egyptians built the pyramids. But both enterprises seem driven by equally arcane national goals. And since the last astronauts returned from the moon, men have been into space, but only into Earth orbit, orbiting around the Earth in the space station. But nonetheless, space has become crucial for all aspects of our lives: navigation, GPS, and environmental monitoring. And astronomy has been hugely advanced by space telescopes. I'll come back to them later. And also, of course, by unmanned probes, which have been to other planets, beaming back from close-up pictures of varied and distinctive worlds. And let me just show a few of these. I've got a few pictures of Mars, the very interesting environment of Mars. Huge craters and valleys. That's a gorge 10,000 meters deep. Here's another huge crater, and I'm going to show you a close-up view taken from one of the landers of the walls of it there. And this is a surface view taken by one of the landers, and this is one taken by the Phoenix lander, which is going to be able to dig to a depth of 1 meter to analyze the soil and see if there might be any evidence of some sort of defunct life there, because there was certainly water once on Mars. Going further afield, Jupiter, the 4 moons have all been observed close up. Especially interesting is Europa, which has oceans covered by thick ice, and here's the ice close up. And Saturn, the Cassini mission went to Saturn, and one of the most remarkable things was what happened next. The Cassini mission launched a robotic craft called Huygens, which was a European craft, which was supposed to land on Saturn's giant moon, Titan. It was supposed to do what's shown in its artist's impression. It was supposed to open a parachute and land on the mysterious surface of this giant moon. And this was robotic on its own. It wasn't controlled from Earth because a light signal, a radio signal, takes hours to get to Saturn and back. And this robot did what was expected, and the left and the center picture show pictures taken on the way down, and the right hand shows where it landed. Now this may look a rather attractive location, lakes and rivers, etc., but the temperature is minus 170 degrees centigrade, and these lakes and rivers are of liquid methane, and those lumps on the right are probably solid methane. Well, this just shows what robotic probes can do, and I hope and expect that during the coming decades, more sophisticated robotic probes will go to all the major bodies of the solar system, bringing back details of what they're made of. But will people follow them? The practical case for sending people into space gets ever weaker with each advance in robotics and miniaturization. In fact, as a scientist or practical man, I see little purpose in sending people into space at all. But as a human being, I am enthusiastic for manned spaceflight, and I do hope that some people now living will walk on Mars. But I don't think this will be politically and financially feasible except as a cut-price venture, perhaps privately funded, spearheaded by individuals prepared to accept very high risks, perhaps even to accept one-way tickets. But that's a subject for another lecture. What I'm more interested in today is whether there is life out there already, rather than whether we will go out beyond the Earth. But I think we know that there's no very exciting life anywhere in our solar system. There may be under the ice of Europa, there may be oceans with something in it, there may be something in Jupiter, we don't know. But let's now widen our gaze beyond our solar system, far beyond the reach of any probe that we can now conceive. We've learnt over the last few decades enough about stars to understand them as essentially gravitationally confined nuclear fusion reactors. And we understand their life cycles, and we can check that against observations. If we see places where stars are forming, this is the Eagle Nebula, 7,000 light years away, where even now new stars are condensing. And we see stars dying. This is what the sun will look like in about 6 billion years, when it blows off its outer layers and leaves a white dwarf behind in the center. Some die less elegantly, like this one, and some die explosively, as supernovae. This is the famous Crab Nebula, the debris from the supernova recorded by Oriental astronomers in the year 1054 AD. the precursor of this explosion was a star at least 10 times as heavy as the Sun. And during its life, it was fueled by fusion of hydrogen into helium, then helium into carbon, oxygen, and up the periodic table. And the material was further processed in the explosion that flung it back into space. And this material flung back into space would then be recycled into new stars. Were this a longer lecture, I would explain all the details of this chart, but essentially this illustrates that in our galaxy there is a sort of recycling ecological process going on where gas condenses into stars, it's processed up the periodic table, then flung back out and condenses then into new generations of stars. And what we can surely say is that before our Sun and planets came into existence, there had been generations of stars which produced all the carbon, oxygen, etc. in our bodies. Indeed, each of us has inside us atoms that come from almost certainly many thousands of different stars from all over our galaxy, which died more than 4.5 billion years ago. We are the nuclear waste from the fusion power that makes stars shine. We've now learned something that makes the night sky much more interesting than it was to our forebears, who looked up at these twinkling points of light and wondered about them. We've learned that many stars, perhaps even most stars, are orbited by retinues of planets, just like the Sun is. We've expected this for a long time because this cartoon shows how we think most stars form. A dusty, slowly spinning gas cloud starts to contract under gravity. As it contracts, it spins up. There's too much angular momentum for everything to go in the central protostar, so it leaves behind a dusty disk. We see this happening in places like the Orion Nebula. We think this is how our solar system formed, and we expected, therefore, that there would be planets around other stars. But only in the last 10 or 15 years have we found direct evidence that that is the case. And even now, these extrasolar planets aren't readily detectable. They're inferred in two ways, and the first way is shown here. If a planet is orbiting a star, then what actually happens is that the planet and the star orbit around their common center of mass, what's called the barycenter. And although we can't see the planet, we can observe the small circular motion of the star. And by taking very precise spectra, it's possible to detect the tiny Doppler shift induced by the motion of the planet, which causes the velocity of the star to give circular motion of typically 10 meters per second. And by this method, one can infer the mass and orbital period of planets. And in this way, several hundred planets have been inferred. This is just a list showing a number of stars which are inferred to have at least 2 planets orbiting them this way. One is known to have at least 5, but there are many, many that are found this way. There's every reason to think that most stars have planets around them. But this technique is only able to reveal large planets, planets which are equivalent to Jupiter or Saturn, the giants of our solar system. But biologists would be especially interested, of course, in possible twins of our Earth. Planets the same size as ours, orbiting other sun-like stars on orbits at a distance from their parent star, such that water neither freezes nor boils. And detecting planets which are Earth-like, rather than giant planets, is of course a greater challenge, because they induce motions of only centimeters per second, rather than meters per second, in the star they're orbiting, and those motions are too small to be detected spectroscopically. But there is another technique that is more promising. one can look for their shadow. And this technique has been carried out by a Kepler spacecraft launched by NASA 2 years ago. The Kepler spacecraft is pointing steadily at a patch of sky in Cygnus, a patch of sky several degrees across, and it's measuring the brightness of 150,000 stars in that part of the sky to a precision of better than 1 part in 10,000. And it's doing that every half hour. The purpose is to detect events when a planet is transiting in front of a star, as shown here. If a planet goes in front of a star, then it blocks out a bit of the starlight, and if an Earth-like planet moves in front of a Sun-like star, it obscures 10 to the minus 4 of the surface area, and so you would expect to see a dip in brightness. And so the signature of an orbiting planet is repeated dips which signal successive passages of the planet. Now, Kepler hasn't been up long enough to detect Earth-like planets. Obviously, you have to wait for 3 orbits, but already it's found tentative evidence for about 1,000 planets, mainly with shorter and closer orbits than the Earth has. And almost certainly it's going to reveal that there are large numbers of Earth-like planets, as well as, of course, the bigger planets which we've already detected in other ways. But, of course, all this is doing, in effect, is finding the shadow of a planet. It's allowing us to find out how big they are. But what we'd really like to do is to actually image them, to see the planets directly, not just their shadows. And that's hard. To imagine how hard, suppose an alien astronomer with a powerful telescope was looking at our solar system from a distance of, say, 50 light years. From that distance, the Sun would look a fairly ordinary star. And the Earth would look, in Carl Sagan's nice phrase, as a pale blue dot, lying very close in the sky to its star, our Sun, and billions of times fainter. So the task is, as it were, looking for a firefly next to a searchlight. It requires great sensitivity and high angular resolution. But if the aliens had a powerful enough telescope that they could detect this pale blue dot, they could learn quite a bit about it, because the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing them. So they could infer that there were continents and oceans, they could learn the length of the day, they could infer something of the climate and seasons. They could perhaps, by studying the spectrum of the light, infer the presence of oxygen and ozone in the atmosphere. Well, 20 years from now, we may be doing studies like that of Earth-like planets around other stars. It'll require either a large array of telescopes in space like this, or the next generation of telescopes on the ground. Look at the scale of the lorry on the bottom left. This is something which European astronomers hope eventually to build. And these will be able to detect Earth-like planets orbiting other stars. Well, will there be life on them? This is, of course, a much harder question. Biology is a much harder subject than astronomy. And I think agnosticism is the only possible stance now, because we know too little to say whether alien life is likely or unlikely. And if for no other reason, that's because we don't know how life began here on Earth. If we knew how that happened, that would give us clues to whether it was likely to happen in any other environment, or whether it was a really rare fluke, like dealing a pack of cards and ending up with them in perfect order. So we just don't know. And for that reason, I think one should search for evidence of life everywhere. Indeed, one shouldn't restrict attention to Earth-like planets, because science fiction writers have suggested other ideas, for instance, balloon-like creatures floating in the dense atmospheres of Jupiter-like planets, swarms of intelligent insects, nanoscale robots, and all that. And I like to tell my students that it's better to read first-rate science fiction than second-rate science. It's more interesting and not much more likely to be wrong, perhaps. Well, even if simple life is found to be common, it's of course a separate question whether it's likely to evolve into anything that we might recognize as intelligent or complex. As you probably know, there are searches being done, the so-called SETI, Search for Extraterrestrial Intelligence, looking for signals that might be unambiguously artificial, something like a string of prime numbers or digits of pi or something like that. I'm glad people are doing this because it would be such an epoch-making discovery that it's worth doing even if one thinks the chances of it happening are very small indeed, and I'm certainly not holding my breath for any success. Of course, there are some people who think that the aliens are out there and are visited, and I get letters from such people. I tell them two things. I tell them first they should write to each other, not to me. And I also say that if the aliens had had the technological nous to come into stellar distances, would they just meet a few well-known cranks, despoil a few cornfields with corn circuits and go away again? It doesn't seem likely to me. But nonetheless, I think one should be open-minded in principle about there being life out there. On the other hand, perhaps such searches will fail. It could be that Earth's intricate biosphere is unique. That would be disappointing to those who are doing the searches, but of course it would have an upside, because it would entitle us to be less cosmically modest, because our tiny planet could then be the most important place in the galaxy. Perhaps even a seed from which life in the far future could spread through the entire galaxy. I've talked so far about stars within our galaxy. Let's now enlarge our horizons further. If you could get 2 million light years away from the Earth and look back at our galaxy, it would look something like this. This, of course, is Andromeda, our nearest neighbor galaxy in space, a spinning disk viewed obliquely where there are 100 billion stars orbiting around a central hub. And our sun would be about 2/3 of the way out towards the edge. And here's another galaxy, the Whirlpool, viewed almost face on. Well, these are an important subject of study for astronomers. And you might ask, how can we learn anything about them? If you're a particle physicist, you can crash together particles at CERN and see what happens, but we can't do experiments. But we can do experiments in the virtual world of our computer. We can ask in the computer what would happen if we crashed 2 galaxies together. And here's an example of what you might see. This is the gravity of every star in one galaxy acting on the others, and you end up with this mess and tidal plumes, etc. Well, you look up in the sky and you find systems like this. And having done simulations of that kind with different assumptions about the mass, etc., you can infer confidently that what's happened here is the 2 galaxies have got close and tidal plumes have been raised by one on the other, and these 2 galaxies may eventually merge. So that's just an example which indicates how we can infer the nature of galaxies by a combination of observations and computer modeling. And we do have huge numbers of galaxies to study. This is a map showing all the galaxies within 600 million light years of us. They're grouped together in clusters, but even in this region there are many thousands. Now, as we turn towards a larger scale universe, we know and have known ever since Edwin Hubble. There he is, heavy smoker there, as you can see. And he showed that the distant galaxies show a spectral redshift. And the further away they are, the faster they're moving away, depicted by the longer arrows further away. Now, this doesn't mean that we're in a preferred central position. I like to give this illustration. Suppose you're on one of these vertices and all the rods lengthen at a steady rate, then the other vertices will recede at a speed proportional to the number of intervening links. And you can imagine this as an infinite lattice, as it were. And that's a good way to think of the expanding universe if you imagine the galaxies, or at least clusters of galaxies, linked together by rods, and the rods all length. There's one feature that isn't depicted by this, but is depicted better by this other Escher picture, angels and devils. This is the fact that the light from distant objects takes a long time to reach us. And therefore, when we look a long way away, we look back in time to an era when everything was more close packed, when the rods were shorter. So what we actually see when we look out into space along our past light cone is better depicted here. The further out we look, the more close packed things are. And we can see very far out. This is a picture which shows a tiny patch of sky. It would take 100 patches like this to cover the area of the full moon. With a small telescope, this would look blank, but with a big telescope, you see these hundreds of little smudges, each one a galaxy, many fully the equal of ours or Andromeda, but looking so small and faint because they are, in many cases, 10 billion light years away. They're being seen when they're still very young. They've got more uncondensed gas in them than present-day galaxies. And we can take the spectrum of their light, and I'll just show you here. This is a tracing of the spectrum of 3 exploding galaxies a long way away. And the only thing I want to point out here is that this is the visible spectrum, and this steep emission line on the right is about 9,000 angstroms, is actually the Lyman alpha line of hydrogen, which of course is normally at 1216 angstroms in the far UV. These are so far away that the redshift is stretching the wavelength by about a factor of 7. The best way to think of this is that the scale of the universe, the rods, have lengthened by a factor of 7 since the light set out. So we can see very far back. But, let me at this stage advertise some new work done by astronomers here, which is on display outside, which shows infrared images of some of these newly formed galaxies, which does show more clearly how stars form in a big burst when galaxies are young. But what about still earlier eras? If we look further back into space, we look back to a time when the whole universe was dense and there were no galaxies at all. As Rav said, cosmologists are sometimes berated for being often in error but never in doubt, but they are quite confident that our universe is the expanding aftermath of a Big Bang nearly 14 billion years ago. And the most compelling evidence, which has really built up since the late 1960s, is that intergalactic space isn't completely cold. All space is pervaded by weak thermal microwaves, the diluted and cooled afterglow of the hot, dense beginning. A dense beginning where there was hot radiation, it expanded, cooled and spread, but it's now still around, raising intergalactic space to 2.7 degrees above absolute zero. 1 second after the Big Bang, everything was at about 10 billion degrees. A mixture of radiation, mainly photons, some protons and neutrons, and also some other particles which make up the dark matter. And it was then almost homogeneous. The word almost is important. So this is a time chart showing various stages, and things become very uncertain right at the beginning. Our present complex cosmos manifests a huge range of temperatures and densities, from the blazingly hot surfaces of stars to the dark night sky. And people sometimes worry when they hear about the Big Bang about how this intricate complexity emerged from an amorphous fireball. It seemed at first sight to violate a hallowed principle of physics, the second law of thermodynamics, which describes an inexorable tendency for patterns and structures to decay or disperse. But the reason that this seeming paradox can be solved lies in the force of gravity, which reverses our normal intuitions. For instance, a star which is self-gravitating has a negative specific heat. If it deflates and loses energy, it ends up hotter, not colder. And gravity enhances density contrasts. So as the universe expands, any patch that starts off slightly denser than average will decelerate more because there's more gravity slowing it down, and its expansion will lag further and further behind, and it'll eventually stop separating out. And this movie shows a computer simulation of part of a virtual universe. It models a domain large enough to make thousands of galaxies. The expansion scaled out, so you see a region staying in the same place, but you can clearly see the incipient structure unfolding and evolving. And in these structures, the galaxy-scale clumps, gravity enhances the contrast still further, and gas will be pulled in and compressed into stars. Movies of this kind portray how galaxies emerged, 16 powers of 10 faster than real time. And each of those galaxies is an arena within which stars, planets, and perhaps life can emerge. We'd like to understand in fuller detail how, from amorphous beginnings, the cosmos evolved its present complexities. And there are various key stages. There must be the first particles, protons and neutrons, the first stars and galaxies, the synthesis of the periodic table in stars, and then formation of planets around later generation of stars, and then, of course, on at least one planet, the formation of a biosphere that led to the emergence of brains capable of pondering their origins. And it's interesting to ask, what are the key prerequisites in a universe if it's to be the arena for this chain of events? Crucial to the whole emergent process, as I've already mentioned, is gravity, which enhances density contrasts. But the important thing about gravity is it's a very weak force, and indeed the weaker it is, the better. It's a weak force in the sense that if you take two protons, the ratio of their electric force to their gravitational force is about 10 to the 36. If you took electrons, it would be 10 to the 42. So that's why gravity is a very weak force, and that's why it's only important on the astronomical scale. But it always wins on a large scale because everything has, as it were, the same sign of gravitational charge. There's no positive and negative. And I like to illustrate it on this picture here, which shows on a log scale radius along the bottom and mass. And see, it's a very, very compressed scale, and it shows the mass radius rates for black holes, and it shows us which have slope 1 on log-log plot, and for solids, which has slope 3 on a log-log plot, the mass going as a cube of the radius. And I want to mention two things. First, because gravity is so weak, a black hole the size of a proton has to weigh as much as 10 to the 38 protons going up there. And if you imagine solids, there's a proton there, and to the right there's an atom. Then as you imagine solids of larger size, a sugar lump, an asteroid, then they are not affected by gravity until you get up to something the size of Jupiter, and then gravity is able to crush them, and then you get into the domain of the stars. This is all straightforward physics, but the important point I want to make is that it's because gravity is so weak that stars are so large. If gravity was stronger, then we'd have a small-scale speeded-up universe where there wouldn't be so many powers of 10 between the arena where gravity is important and the arena where microphysics operates. So gravity is crucial, but the weaker the better. So let me just run through other requirements for a universe that involves complexity. First, clearly, departure from thermodynamic equilibrium. If the universe had collapsed while it was still in thermal equilibrium, then nothing of complexity could have ever happened. Then there must be matter-antimatter asymmetry. Otherwise, as the universe cools down, all the matter and antimatter would annihilate, and you'd have just radiation, no atoms. Also, non-trivial chemistry. If we had just hydrogen, there'd be no possibility of complexity, and this, of course, requires the well-known tuning between the nuclear and the electromagnetic forces, which is not yet understood by physicists. And, of course, the process has to allow stars to form, and indeed second-generation stars, because the first-generation stars will only be hydrogen and helium, and you've got to have a second generation of stars with processed material if you're to get planets and life. And a tuned cosmic expansion rate. If the expansion rate was too slow, the universe would collapse too soon. If it expanded too fast, then gravity wouldn't be able to pull things together again, as I showed they did in that movie. So all these things have to be fulfilled. And the other final thing is that the early universe can't be completely smooth. Otherwise it would now, after 14 billion years, be just cold neutral hydrogen, uniformly distributed, no stars and no people. So there must be some fluctuations which gravity can then feed on, as in the movie. And one of the triumphs of the subject is that the fluctuations in the early universe have been observed by measuring the spectrum of the background radiation with a precision of 1 part in 100,000 across the sky. And those fluctuations, if you feed them in as initial conditions to a computer simulation, then give rise to structures with just the scale we observe today. So there's a link between what we observe in the early universe, just small delta over rho fluctuations, and the present universe. That matches together, vindicating the idea that cosmic structures evolve via gravitational instability in the expanding universe. Well, what we don't yet know, of course, is what set up these conditions, what set up those fluctuations, and what set up the mix of matter, radiation, and other particles that the universe is made of. As I said, we can trace cosmic history with some confidence back to 1 second, indeed back to about 10 to the 9 seconds, because back then particles have about the energy you could produce in the LHC. And back at that time, the entire observable universe would have been the size of the solar system. Very, very dense. But questions like, where did the fluctuations come from, and why did the early universe contain the actual mix we observe of protons, photons, and dark matter, take us back to the brief instance when our universe was hugely more compressed still, to when energies and densities were so extreme that experiments offer no direct guide. And indeed, when the universe was a trillionth of a trillionth of a trillionth of a second old, that's when key processes are thought to have happened, and the universe was then literally that big. And many scientists talk with a straight face about the physical process that happened at that stage, which gave rise to the present properties of our universe, its expansion rate and its fluctuations. Well, at this point, or perhaps sooner, I should insert a sort of health warning. I'm getting a bit speculative. And I now want to mention a couple of other speculative issues. One is, how extensive is physical reality, which scientists can talk about? And the point I want to make is that it could be a lot bigger than what we can see. As I mentioned, we can see galaxies out to about 10 billion light years away, but that's still a finite number. And it's finite because there's a kind of horizon, a shell around us, delineating the distance light can have traveled since the Big Bang. But that shell around us has no more physical significance than the horizon if you're in the middle of the ocean. And on the ocean, you don't think the ocean finishes just beyond your horizon, and there's no reason why our universe should end just at this horizon. In fact, there's a strong reason for thinking it goes on thousands of times further. That's because the background radiation, if you look that way and that way, is different by less than 1 part in 100,000. So it certainly goes on, or almost certainly goes on, much, much further, and some speculations say it goes on so much further that every combinatorial option is fulfilled, and there'll be other replicas of this lecture room somewhere elsewhere, but that's far, far, far beyond anything we could ever observe. But the volume of space-time within range of our telescopes, what astronomers have traditionally called the universe, could be only a tiny fraction of the aftermath of our Big Bang. But that's not all, because our Big Bang may not be the only one. There are two options. There's one idea that there could be separate three-dimensional spaces embedded in a common higher dimensional space. And just as you could have some ants crawling around on a sheet of paper, their two-dimensional universe, being unaware of another population of ants on a parallel sheet of paper, so there could be another universe just that far away from ours. But if that distance is measured in some fourth dimension and we're imprisoned in R3, we wouldn't know about it. That's one idea. And another idea is what's called eternal inflation, that our universe and its horizon is there, but there could be a whole lot of big bangs bubbling away. And these ideas have been developed mathematically, but we don't know the physics that prevails at this ultra-early stage. But it could be that our Big Bang is just one patch of space-time in a vast cosmic archipelago. And indeed, a challenge for 21st century physics is to decide whether there have been many Big Bangs rather than just one, the first in the decision tree, and then, if there are many, to ask, are they all governed by the same physics? Or do they have different physics? As what we call the laws and constants of physics are just, in this grander perspective, just parochial bylaws in our cosmic patch. And many string theorists do suspect something like this. And if so, the Big Bangs might ring the changes on all the options, and then it would occasion no surprise that there was one Big Bang fine-tuned enough to allow the chain of events that led to the emergence of our biosphere. But we don't know about this, but I would emphasize that it's speculative science, but it's still science and not metaphysics. If I needed a logo for my research area, I'd choose this, an Ouroboros. The image depicts the interconnectedness of the microworld on the left and the cosmos on the right. The inner space of atoms and the outer space of the universe. There are links between small and large, left and right. Our everyday world of life and mountains is determined by atoms and chemistry. And higher up, stars are powered by fusion of nuclei within those atoms. Higher up still is another left-right link. Galaxies are seemingly held together by swarms of subnuclear particles that make up the dark matter. The left is the domain of the quantum. On the right-hand side, Einstein's gravity holds sway. And general relativity and quantum theory are the two pillars of 20th century physics. But they haven't yet been meshed together into a single unified theory. And in most contexts, this doesn't impede us because the domains of relevance don't overlap. Astronomers can ignore quantum fuzziness when computing the orbits of planets because they're so big. Conversely, chemists can safely ignore the gravitational pull between the atoms in a molecule because they're 40 powers of 10 feebler than the electric forces. But at the very beginning, everything was squeezed so small that quantum fluctuations could shake the entire universe. So to confront the overwhelming mystery of what banged and why it banged, we need to understand the synthesis at the top of this Ouroboros between the two frontiers, the very large and the very small. And that's what string theorists and others are working on. But before leaving this picture, I want to emphasize the third frontier of science. Not the very large or the very small, but the very complicated. Cells, people, and mountains. And it's on this third frontier, the very complex, that 99% of scientists and all biologists are working. Even an insect, with its layer upon layer of complexity, is harder to understand than a star, where intense heat and compression by gravity preclude complex chemistry. This, of course, is the famous flea drawn by Newton's least favorite FRS, Robert Hooke. We ourselves are midway on a log scale between atoms and stars. Large enough compared to atoms to have layer upon layer of intricate structure, but not so large that we're crushed by our planet's gravity. Indeed, the geometric mean of a proton mass and the sun's mass is 50 kilograms, not too far from the mass of most people here. So the message of this picture is that to understand ourselves, we must understand the atoms we're made of, but also the stars that made those atoms. Finally, I want to draw back from the cosmos, from what may be even a vast array of cosmoses, governed by quite different laws, and focus closer to the here and now. I'm often asked, is there a special perspective that astronomers can offer to science and philosophy? Well, we view our home planet in a vast cosmic context, and in coming decades we'll know whether there's life out there, both fascinating questions. But I think we can offer a more distinctive insight, and that's an awareness of an immense future. The stupendous time spans of the evolutionary past are now part of common culture, unless you live in Kansas or Alaska, perhaps. We know that our present biosphere is the outcome of about 4 billion years of Darwinian evolution. But most people still somehow think that we humans are necessarily the culmination of the evolutionary tree. And that hardly seems credible to an astronomer. As this time lapse illustrates, our sun formed 4.5 billion years ago, but it's got 6 billion years more before its fuel runs out. It then flares up, engulfing the inner planets. It's less than halfway through its life. And the expanding universe will continue, perhaps forever, destined to become ever colder, ever emptier. As Woody Allen said, eternity is very long, especially towards the end. So, any creatures witnessing the sun's demise 6 billion years hence won't be human. They'll be as different from us as we are from a bug. Post-human evolution, here on Earth and far beyond, could be as prolonged as the Darwinian evolution has led to us. And Darwin himself was aware that there was evolution in the future, but we now would suspect that that evolution will happen on a faster time scale than natural selection, may be driven by technology. But my concluding thought is this. Even in this concertina time span, extending billions of years into the future as well as into the past, this century is a special one. It's the first in the 45 million centuries of our planet's history when one species, ours, has had Earth's future in its hands and could jeopardize life's immensely long-term potential here on Earth and perhaps far beyond. So, this pale blue dot in the cosmos is a special place. It may be a unique place, and we're its stewards at a especially crucial time. And that's a message for us all, whether we're interested in astronomy or not. Thank you very much.